So this is the virtual values of voltage and current. Together they are also called as apparent power. So in very simple terms, we can say that a transformer, which means it transforms something into something else. So which converts low voltages into high voltages is known as a step-up transformer. EP will be equal to NP negative d phi by dt. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we were dealing with alternating current and various factors relating to an LCR circuit. So we are going to step up a notch and we are going to learn about something you might have seen in every day of your life, but you never really thought about it. So let's get right on to it. So before actually getting into the real topic, that is a surprise. So before that, I wanted to just tell you about a few minor points we actually left out in the previous derivation. That is, in the previous derivation, one common doubt was that how did cos minus phi in the equation suddenly became cos phi? The simple explanation is that cos minus theta is actually equal to cos theta. That is why we never considered the negative sign. That is why even though the negative sign is taken outside, later I disregarded it. Cos of minus theta is actually equal to cos theta. That is why in the average power equation, it is just Vrms into Irms into cos phi. Now, since we are talking about the terms of power, I thought I'll introduce you to power factor. So what exactly is this power factor? So for that, we need to take down the equation for power once again. So we do know that P average. In last class, we derived what P average was. So P average is actually equal to Vrms into Irms into cos phi. So this is the equation for average power produced in a series LCR circuit. So what this actually means is that this particular power is also known as apparent power, and this particular power output, that is the net output we get, is known as true power. So the equation actually states that true power is equal to apparent power times the power factor. So this cos phi is known as power factor. So the thing you have to understand is that, so this is the virtual values of voltage and current. Together they are also called as apparent power. So actually the true power will be equal to apparent power times the power factor. So from this, it's very simple now. So in order to find out what is power factor, it's very simple. That is cos phi. We are just trying to find out what cos phi is. What is the phase angle difference and the cos of the phase angle difference. That is the only thing we are trying to find out in this particular equation. And that particular cos phi itself is known as power factor. So it comes from the equation true power is equal to apparent power into power factor. So true power is the net power output we get, and apparent power is nothing but voltage times current. That is the RMS values of voltage times the RMS values of current. So cos phi will be equal to P average, that is true power divided by apparent power, which is Vrms into Irms. That is the equation to find out cos phi, or simply power factor. We can also use one more method, that is using the impedance triangle. If you use the impedance triangle, we know that from the previous sessions that this will be the impedance triangle, where the hypotenuse will give you impedance and here it will be resistance, and the altitude will be nothing but XC minus XL, or simply we can say that it is chi C minus chi L. So some textbooks actually denote chi C minus chi L as simply as XC minus XL. Both are fine as long as you understand the meaning behind that particular concept. So again, if this angle is phi, then automatically we can find out what cos phi is. So if in some cases they are giving you the values of resistance, capacitance and inductors, disregarding the values of the net impedance, or if they are giving you certain quantities and not giving you a clear cut information about impedance, you can actually use this particular relation in order to find out the power factor, that is cos phi. So you know that cos phi is actually equal to, cos theta is equal to adjacent side by hypotenuse. So simply you can write it down as adjacent side, that is r divided by z. You can find it using cos phi is equal to r divided by z. So simply you can have the angle. If you know this particular relation, then also you can find out what is this. If more information is given, that is, if information about impedance is given, then directly you can write z is equal to root of r square plus chi c minus chi l whole square. So you can use that relation also. If you want to find the angle, then that is also easy. Phi is equal to, simply phi is equal to cos inverse r by z, or you can substitute the values for z and you will get the power factor. The question is to find the angle, that is the phase angle. Then you can just use cos inverse r by z and then you can directly take what the angle is. So that's all about power factor. And now the main theme of the day, that is the surprise that you see every day but you disregard. So transformer, not the Transformers movie, but what exactly is the transformer that is near your house? Every street there will be a transformer. You might have seen or heard hissing noises. You might have seen one big box with several wires passing through it. So what exactly is a transformer? What is the job of a transformer? Why is it there? So that is what we are going to study in this particular topic. So we are going to learn about what a transformer is. So in very simple terms, we can say that a transformer, which means it transforms something into something else. So we can say that a transformer can transform alternating voltage into its different values. That is, if it can convert high voltages into low voltages, and sometimes it converts low voltages into high voltage. So in one word, we can say that, in a nutshell, we can say that a transformer will change the alternating voltage. Okay, the transformer is designed to change the alternating voltage. If we input one voltage, the transformer will give us an output of a different value of voltage. So that is what a transformer actually does. So how does this particular transformer look like? So the modern transformers will have several layers to it, several windings to it, all is there. But the basic principle that paved way for all this innovation came from one simple model. And that one simple model is what we are going to see right now. So we do know that transformer converts high voltages into low voltage or low voltage into high voltage. So how does it do that? So the very simple explanation is that there will be an input terminal, right? There will be an input. So let's say this is the input. And automatically, if there is an input, there should be an output. So I'm saying that this will be the output. So we have an input and we have an output. So what are we inputting? It's very simple. So now you actually know how current is generated, how alternating current is generated, how it is passed through the lines, how current actually behaves, how current is added up and it is leaving a junction, entering into a junction, all that, all these things you have already studied. Now, for this current to enter into your homes, it needs to be transmitted across a long distance. Sometimes the current will have high values. That is why you can see thick lines in the post. So, but the current that is entering into your house is not a high value current. It is actually a low value current with having high voltage. That is actually Ohm's law, which is allowing us to do this. So again, what a transformer does is that, usually what it does is that, if the current is coming to your homes, it is entering into your homes, what a transformer does is that, it will take this high value current and it will convert it into low value current. How it does is that using voltage. Instead of actually losing current or voltage, what it does is actually that it uses Ohm's law, or simply the very simple definition is that once a high value current reaches here, automatically power is equal to VI, which means automatically the current, if the current is high, the voltage should be low to like have a stable power output. right? So when current is having a high value, what a transformer does is that it will take that current and make it into a low value, which means the voltage will be lower in the input and in the output, the voltage will be higher. Simply that is what a transformer does. So the working principle behind this is actually mutual induction. You can actually see here that there is no connection in between these two coils. It is just one frame and just some windings around that particular frame. So this particular framework and this particular windings has its names. So basically this input terminal where this input happens, this particular input terminal or the windings or the number of turns in this particular input terminal is known as primary input coil, or simply this is the primary coil. So this is the primary coil, and automatically we know the name of the other coil, that is the output coil. It will automatically be the secondary coil. So we have a primary coil and we have a secondary coil. And one more important discovery or observation we have to make is that the primary coil, you can see here in this particular transformer, the primary coil number of windings is less when it is compared to the number of windings in the secondary coil. Now, why is this happening? How is the transformer made? What are the other parts of it? All will be explained right now. So again, before getting into the diagram and the construction of this particular transformer, you have to understand how a transformer actually functions. So the functioning of a transformer is very basic. That is, you have already studied about what mutual induction is. So if I induce a change in this coil, then automatically an EMF will be induced in the other coil. So we are controlling that particular induction process. That is, the EMF being induced, or basically just voltage being induced, is being completely controlled by this primary coil. So depending on the amount of voltage or current entering into this primary coil, there will be an EMF induced in the secondary coil. So with the number of windings, we are controlling what is the voltage output of that particular transformer. So again, the transformer simply works on the basis of mutual induction. So transformer is a device that is, it is the application principle of mutual induction. So transformer is an application of mutual induction, and based on its conversion, is high voltage being converted into low voltage or low voltage being converted into high voltage, the transformer is actually divided into two categories. So one is step up transformer and one is step down transformer. So what a step up transformer does is that it converts low voltages into high voltages. So which converts low voltages into high voltages is known as a step up transformer. So it converts low voltages into high voltages. So it is stepping up. So that is why it is called as a step up transformer. And which converts high voltages into low voltage is known as a step down transformer. So those are the very two type of transformers which you have to understand. So first, it's very simple. What is the working principle behind a transformer and what are the two types of transformers you have to understand. And then this is the basic diagram of a transformer. That is, there will be an input into the primary coil which is wound around a frame. So this particular frame is actually made up of soft iron core. So this is actually made up of soft iron core material. So you can say that there will be an input, which is the primary coil. There will be an output, which is the secondary coil. And these two coils are actually wound around a conducting soft iron frame. So again, how do you actually construct a transformer? It is very simple. First, we start with a basic diagram. So there is a rectangular frame here, which is made up of soft iron core material. So I can just say that, okay, this is soft iron core. So it is a soft iron core frame, and then you have windings on both sides. So again, we know that this particular part is known as, that is the input part is known as the primary coil. So I'll call this part as the primary coil, and this will be the secondary coil. So we have the primary and the secondary coil there. Now, we do know that whatever we are inputting, that is a voltage source that we are inputting, that we are going to convert into high voltage or low voltage, meaning this can be a step up or step down transformer based on the number of windings and the process it is doing. Or simply I can say that the voltage which is entering into, generally I am saying the voltage which is entering into the primary coil, that is the voltage that I am inputting into this primary coil, is known as primary voltage. So it is indicated by Vp. Vp means voltage in primary coil. And now automatically, if this is Vp, that is the primary coil voltage is indicated by Vp, automatically the secondary coil voltage will be indicated by Vs. So we can see that Vs will be voltage in secondary coil. And then, since voltage is out of the way, the next thing is the number of turns. So we do know that number of turns has to be higher or lower depending on if it's a step up or step down transformer. So we can say that the primary number of turns or the number of turns in the primary section, I can indicate it as NS and NP. So NP will be number of turns in primary, number of turns in the primary coil, and NS will be similarly number of turns in secondary coil. So NS is the number of turns in the secondary coil, NP is the number of turns in the primary coil, Vs is the voltage in the secondary coil, and Vp is the voltage in the primary coil. So let's say this will have a voltage of Vp, this will have a voltage of Vs. The number of turns in the primary coil is indicated by Np, and the number of turns in the secondary coil is indicated by Ns. So we have that particular relation because we know the number of turns and the voltage entering will actually affect the output value. So that is why these two factors are very critical. So again, we do know that transformers, that is, this particular transformer can be divided into two sections. One can be a step up transformer, one can be a step down transformer based on its function. Is it increasing voltage or is it decreasing voltage? Based on that, automatically it will be a step up or step down transformer. So how do you know which one is a step up or step down transformer? There is an easy trick to it. So we can study that using a simple table. So if it is a step up transformer, then I can say that the number of turns or the voltage in the secondary coil, let's start from voltage. A step up transformer means that it is increasing the voltage, right? So obviously the output voltage should be high. So we can say that the voltage in the secondary coil should be greater than the voltage in the primary coil. That is very easy, right? The characteristic of a step up transformer is that Vs should be greater than Vp. And the next characteristic obviously is number of turns in the secondary coil should be higher than the number of coils in the primary. The number of turns in the secondary should be higher than the number of turns in the primary coil. The final one is very easy, that is current. So what happens to the current? We told all about the voltage and number of turns. Now we have to tell about the current value. So obviously if voltage is going up there, it means current is automatically reducing or decreasing. So I can say that IP will be greater than IS. That is, current in the primary coil will be having a greater value compared to the output value, because when it is entering, it is high current and low voltage. When it is exiting, it is high voltage and low current. So that is how that particular relation happens. And for step down transformer, it is again easy. You just take the ulta. So again, step down transformer, which means that it is going to reduce the voltage output. So high voltage is coming in and you have to decrease the voltage level and increase the current level. So we can say that Vp will be greater than Vs. That is, the voltage that is entering into the primary coil will be great and the voltage that is exiting from the secondary coil should be low, which means we are trying to increase the amount of current that is produced. So we are saying that for a step down transformer, that is, we are going to step down the voltage. So we can say that voltage in the primary will be greater than voltage in the secondary coil. And simply next topic is number of turns. Number of turns in the primary coil should be greater than the number of turns in the secondary coil, because always remember it's an easy relation. If there are more number of turns, then automatically more EMF will be induced, which means more voltage will be produced. If you have more windings on one side, automatically it means that higher voltage is going to be produced in that particular side. Okay, so we say that NP should be greater than NS. And finally, we know that current is the factor we are trying to increase here, which means the input current, that is, the input current will be low and the output current should be high. So the current in the secondary coil should be higher than the current in the primary coil. So this particular relation is what defines a step up and step down transformer. That is, for a step up transformer, voltage should be high in the secondary coil, that is in the output coil, which also means number of turns should be higher in the output coil, which means the current should be lower in the output coil. That is what this relation states. And for a step down transformer, completely opposite. That is, the input voltage should be high, the input number of turns should be high. That is, the number of turns in the primary coil should be high, the current in the primary coil should be low, which means only then we'll get the higher output. So that is regarding step up and step down transformer. It is very simple. You just need to know how to construct it, how it works, and on what principle that particular thing actually works on. So you have a soft iron core frame and just some coils wound around it, and you can actually produce EMF. That is the great thing about physics. So in a nutshell, that is all about transformers. I'll give you a definition about how it actually functions, or the working principle of a transformer. So again, this is not complete. This is the basic principle or the basic figure which you need. In actual cases, it will be laminated, it will be covered, the bindings will be more, and the sections will be separated. That is all for practical applications. Why that happens, I'll explain very soon. But again, why we use a step up and step down transformer is that in our homes, that is in our day-to-day lives, we go to our homes, we plug in our charger, we plug in some electrical appliances. We don't need a huge amount of current. They work on low current and high voltage. So for that purpose, the current which we receive in our homes is actually low current and high voltage, a voltage of up to 220 to 250 volts. That is the voltage levels we get in our homes. So for that, we take the higher value currents and convert it into lower valued currents, that is higher voltage currents. And here, step down transformer, just because we need higher voltage and lower current does not mean that the entire world needs higher volt and lower current. That is some factories. If you have any factories that is functioning near houses or near any plants or any open spaces, you actually need higher amount of current because you need to operate heavy machinery. For that, you can actually use step down transformer, which actually reduces voltage and increases power, that is current. So again, the last part, that is the working principle behind a functioning transformer. So again, these are all the basic things you already know. That is, the transformer will consist of two sets of coil, that is the primary and secondary coil, and it is being wound around a soft iron core which is laminated or laminated soft iron core. So two windings will be there, one will be primary and one will be secondary, which act as the input and output. And then AC voltage to be altered, which means that the alternating current which has to change. The voltage should change, right? It should either increase or decrease. That particular AC voltage is being fed into the transformer, that is into the primary coil, which acts as the input. So we are feeding AC voltage which is to be altered into the primary coil, and then when we are doing that, automatically there is a magnetic flux being generated. When current is flowing through a solenoid, automatically magnetic fields are generated. And if you place one more solenoid or just a wire which is having number of turns, just beside that, mutual induction happens, which means an EMF will be induced on the other coil. So that is what is happening here. A change in magnetic flux induces an EMF in the secondary coil. So this particular induced EMF is what we are taking out as voltage. So EMF just means voltage. That is how the transformer actually functions. Now, the final thing is that, I promise this is the last thing, we just need a mathematical equation to write down so that whatever theory we just wrote down, it is validated. So we need a mathematical proof also. So I am considering an ideal transformer because the entire input is converted to output, there is no loss, it is perfectly wound, it is not loose, like that, an ideal transformer. So if I am considering an ideal transformer, then I can say that the EMF induced E or EMF induced E will be equal to, we already seen the equation from the previous chapters, that is E is equal to, simple, negative d phi by dt. We have already learned this, and if there is n number of turns, this equation will be written like this, right? This is the general representation of an EMF, that is a change in magnetic flux. This phi indicates the change in magnetic flux, d phi by dt. The flux is changing with respect to time. So a changing magnetic flux will in turn produce an EMF or simply a voltage. So this n is nothing but the number of turns. So generally I can write E is equal to n d phi by dt, and then I can say that EP will be equal to NP negative d phi by dt. Also ES will be equal to NS into negative d phi by dt. So this is in terms of the primary and secondary coil. If there is any change in magnetic flux associated with the primary coil, then automatically there will be an EMF induced in the secondary coil and vice versa. So since here we are dealing with voltages and not EMF, we can directly say that here this particular E will be equal to Vp, or this will be equal to Vs, because we are dealing with voltages and not EMFs. So that is, EMF actually means voltage itself in loose sense. So we can say that Vp is equal to Np minus d phi by dt and Vs is equal to Ns d phi by dt. Now if I name these as equation 1 and equation 2, then I can form a relation between these two quantities. That is, if I am saying that I am to divide equation 2 by equation 1, then I can say Vs divided by Vp will be equal to Ns divided by Np. d5 by dt will cancel each other out, and we'll have this particular relation for an ideal transformer. So if we have or we know the voltages or the ratio of voltages between the primary and secondary coil, then automatically we'll get the ratio of number of turns in the primary and secondary coil. You can use this to solve numerical problems. So this is a mathematical relation for an ideal transformer. Again, if they are giving currents in terms of or instead of voltages, then again the same relation actually also exists for currents also. That is, this will be again equal to Is divided by Ip. Instead of voltages, it will be currents. So again, it is the same thing. If they are asking for numericals, you can use this particular equation to solve those numericals. So we are moving on to the final steps of this particular chapter. We are going to see what an efficiency of a transformer is and what are the practical losses that a transformer actually faces. So efficiency just means that how efficiently you work. If I'm inputting something, am I getting the net output as the exact same things I have inputted? If I fill a car with 1 liter of petrol, am I getting the same amount as output? No, right? Obviously, when an engine functions, some things will be lost as heat, some things will be lost as some form of energy will be lost as vibrations, or some will be lost as kinetic energy or potential energy. Like that, many forms of losses will present. So if you fill your car with 1 liter of petrol, it is only 40 to 48% of efficiency you're getting. Other part is lost as vibrations, it is lost as heat, it is lost as kinetic energy, and all these losses will be there. Rotational, translational, many forms of energy conversions are happening in that particular place. So efficiency means it is a ratio of input to output. That is, how much output are we getting to the quantities which we have inputted. Or in terms of a transformer, which is the fuel is, or which the input quantities are voltage and current, we can say it in terms of power. How much power output are we actually getting? How much efficiency, how much power efficiency are we getting? So we can say that it is the ratio between output power divided by input power. So we do know that power is given by Vi. That is, Vi will be the equation for power in an electrical circuit. This is the primary thing we do know, and we also know that we are speaking in terms of a transformer here. So automatically V and I, that is the output part of voltage and current, will be in the secondary coil, right? So automatically efficiency eta, efficiency is indicated by the Greek letter eta. So efficiency will be equal to output voltage, that is voltage in the secondary coil, times current in the secondary coil, that is output power, P is equal to Vi. So voltage in the secondary times current in the secondary divided by input power. So it will be in the primary coil. Automatically it will be Vp IP. So Vp times Ip. So this is the efficiency equation that is used to find out the efficiency in a transformer. So ideal transformer, that is 100% efficient transformer, whatever input we are giving, we'll get it as output. The ratios will be equal to 1. If you're giving 100 grams of fuel and you're getting 100 grams of output, we can say that, or 100 joules of energy you're putting in and 100 joules you're getting output, then you can say that the net efficiency is equal to 1. It is an ideal condition, which is not practically possible, which means there will be some form of losses. So we can see that the efficiency of any machine will be less than 1. As it approaches 1, we can say that, okay, that machinery is, or that particular equipment is really efficient. As it approaches 1, it means that denominator is getting itself nearer to the numerator. Whatever we are inputting, we are getting as output. So as sooner or as closer it reaches the value of 1 unity, then we can say that okay, it is highly efficient. If it is a low number, if it is like 0.00001, then we can say that it is not likely that efficient, because the denominator value is higher, which means we are giving a lot of input and we are not getting enough output, which means it is not really efficient. So we are going to see what are the possible losses, that is inefficiency in a transformer. So what are the possible inefficiencies that can arise in a transformer? It is very easy. Whenever you pass current through any electrical circuit, the obvious result is heat. So heat will be produced in a transformer. So in a transformer, huge amounts of current or voltage is passing through the primary and secondary coils. Automatically, it means that there will be high amount of heat energy produced. In thermodynamic sense, we should only say heat, but okay, there will be high amount of heat produced. So I can say that there will be heat loss or simply copper loss. So this is known as the loss of energy in the form of heat inside a transformer. This can be actually rectified by using thick wires. If we generally we use copper wires, that is why it is also known as copper loss. So if you use thick copper wires, then we can say that the heat loss can be controlled or it can be reduced. There will obviously be heat loss because heat is coming because there is resistance inside the wire. It is a practical effect. We cannot do anything about it. We can only minimize it to a certain extent. So we can say that heat loss can be controlled using thick copper wires. And the next thing arises is very simple. You know that the flux, interchange of flux, the change in magnetic flux, inducing the flux or inducing the EMF in the other coil happens because there is a tightly wound wire, right? There is tightly wound wires there. So we can actually say that this particular magnetic flux in that coil can actually leak out. So that particular leakage of flux which causes efficiency loss, that is, if the entire flux is not contained within the coil, it cannot efficiently induce EMF in the secondary coil, which means that if flux is not contained, efficiency will decrease. Or we can just say that flux leakage is one more problem in transformers. This happens when phi B, that is the magnetic flux phi B cannot fully enter into the secondary coil. This can arise due to two main reasons. One main reason is that it is because of poor design. If the wires are or the windings are too far apart, it is very difficult because the magnetic field will lose its strength as distance increases. So it can be due to poor design or this can be due to any other internal reasons, that is mainly loosening of these windings. So it can be actually improved by having an efficient design and tightening the windings or tightly wounding the coils. So that is the fix for flux leakage. And finally, one more is that eddy currents. So I have already told you what eddy currents is. Small currents that is forming, small amount of current that is forming on the surface of flat metals when there is a change in magnetic flux. Induced EMF will produce small eddies or small current eddies in the particular soft iron core material in this particular frame. And now this will try to oppose the voltage that is being generated in the secondary coil. So that is eddy currents. So we can reduce this by using laminated core material or simply by laminating the soft iron core, making it into thin sheets. All this can be done in order to reduce eddy current loss. So these are the three main losses you face inside a transformer, and mainly this will be enough. There are further losses. If you want, you can also research on them and write those also, but these three will be definitely enough. So to sum up, we learned about transformers and we learned about what power factor is. I hope you have understood everything about transformers and power factor. I'll be here in the next class with a new topic. Until then, thank you.